Operation Classroom. We are now discussing GATE 2023, question 32. I am Shekhar Bhattacharjee. Burning of methane in a combustor. So this is a combustor. We'll look into it. It is carbon monoxide, carbon dioxide, and water vapor. And methane is used as a fuel. So let's quickly look into the schematic diagram. So let's say this is let's say some kind of a furnace here. So this is where the fuel and the air mixture comes in. And this is where the flue gas goes out to the stack. And the ambient air that exchanges heat with the stack gas. Otherwise, this heat would have been lost to environment, which is not desirable. So this there's a heat exchanger, and it gets heated up. So this warm air comes in and mixes with the fuel here. In this case, this is methane for us, and this goes into with some kind of a control. It goes and there's a combustion here. And what is the purpose? So this is a high temperature, let's say around close to 1000 degrees Celsius. So there could have been some kind of a catalyst, etc. But for lower temperature, let's say we have some kind of a process fluid. So let's say around 400 to 500 degrees Celsius, a process fluid, and that is heated up, and this is sent to the actual process where it is required. Okay, so basic purpose is to heat the process fluid. Now, when there is a combustion here, when there's a combustion, what happens? Let's say in the case of methane, it reacts with oxygen. Of course, there will be some nitrogen also when we are using air in the 80:20 ratio. So all carbon goes to carbon dioxide, and the hydrogen goes to form water. Of course, there will be certain amount of carbon monoxide would be formed by this reaction also. And had there been any sulfur, that would have formed some kind of sulfur dioxide, sulfur peroxide, which we call as SOx. Okay. And probably if there's if from the nitrogen, some NOx also formed, nitrogen dioxide, nitric oxide, nitrogen dioxide, those oxides are also formed. But those are beyond this question. So we have to find out the theoretical oxygen requirement. Another thing is methane is fed to the combustion at the rate of 100 moles per hour. So at the rate of 100 moles per hour, of which 50% reacts. So if of this one 50% reacts and 50% goes out as it is. Okay. So here, so 50 mole, because 100 mole is coming, so 50 mole reacts to form carbon dioxide, carbon monoxide, etc. We have to find out the theoretical oxygen requirement. So for that, we have to understand what is called complete combustion. For complete combustion, we assume all the carbon goes to form carbon dioxide, and all the hydrogen goes to form water, and all the sulfur goes to form sulfur dioxide. Of course, we don't have sulfur here. So here we'll not consider this reaction at all, although this is actually occurring. But for theoretical oxygen requirement, we assume this reaction only when all the carbon that is present in 100 mole, does not matter how many percent it reacts, all the carbon goes to form carbon dioxide, and all the hydrogen goes to form water. So theoretical oxygen is always calculated based on complete combustion, which is this one. It does not matter how much percentage reacts. So if you have 100 mole here, of course we need 200 moles of oxygen. Okay. And of course, if you want to find out the air requirement, so we have to multiply we have to multiply 1 over 0.2. So that gives you total amount of air required. And of course, to this, of course, there will be nitrogen also. Okay. So the answer is for 100 mole, for 100 mole of methane, theoretical oxygen requirement would be 200 moles. So that is my answer. Now, this is a very important parameter. in chemical engineering applications in a relative refinery, natural gas fired burner, or for the boiler load, this keeps on changing quite often here, depending on this process fluid load. This heat requirement keeps on completely changing. So there is a control system which calculates the theoretical oxygen requirement, and there's slightly more to it, maybe around 20%. And of course, to that, of course, correspondingly, it's in the same nitrogen, in that proportion, nitrogen will be added to ensure complete combustion and avoid carbon monoxide formation. If the airflow is much greater than the theoretical, is much less than the theoretical requirement, then of course there will be increased production of carbon monoxide, less production of carbon dioxide, and there'll be smoke and soot formation will be higher, and the flame stability will go down, and there'll be carbon monoxide in stack, which is not desirable. If the air sent here, if the air is much higher than the theoretical oxygen requirement, then there will be extra nitrogen. And this, of course, as you can see, the nitrogen does not contribute to anything. So what it really does, it takes away the sensible heat from this air and just goes out. So that is not again desirable. So if there is much higher air passing through than what is required that means theoretical oxygen, theoretical air requirement, then there will be extra nitrogen and oxygen in the stack, and that will result in low boiler efficiency, okay, or low fuel efficiency. Flue, and normally what we do these days, we put flue gas oxygen sensors or carbon monoxide sensors also these days. So, and accordingly, they send the signals over here, and they correspondingly change the so let's say this is a ratio controller, so that changes this particular ratio of fuel to air so that we get the maximum efficiency. Anyway, so this is my answer.